something I thought we could do, but if you've done that already, then there's no need.
Well, it's done rather quickly, so it might not be a bad idea to.
I could do it again.
Maybe you
Remind-
doing it.
remind
You
us.
did the
No, I don't think I do. I have one way of doing it, which is not. It takes too long somehow. There's one idea, but then you have to check things, and it doesn't quite fall apart as obviously as I'd hoped.
you did it for complex field.
Yes, I did it for complex field, but this formula is also true for the
For real.
for real.
So that's something we could do. Okay. So if H is a subgroup of G, and I'm thinking about actually finite subgroup. And the dimension of the fixed point space of H is 1 over the order of H times the sum over elements little h and capital H of the trace of the matrix representing the element little h. Okay? So I could prove this, which is a kind of interesting statement because it says I can do some calculations involving only the group and the representation that I picked and extract a piece of information which is useful in terms of my bifurcation problem, this dimension of a fixed point subspace. Where I thought it might be useful to go more generally today is to talk about oscillatory bifurcations and to present the kind of the result that's analogous to the equivariant branching lemma, but for the oscillatory case. That's the equivariant Hopf theorem. And the setup is very similar. There are a couple of differences just because we're dealing with time periodic solutions, and we need just to kind of point out some of the differences, and then to do an example of that. And the natural example to do for that, given that we did D3 symmetric steady state bifurcation, would be to do D3 symmetric Hopf bifurcation. And that has its own kind of intrinsic interest. And I suppose in a sense it doesn't, parts of the setup obviously do relate to what we know about D3 steady state, but then some of the conclusions look very different, and so it's not clear to me that that has a direct liquid crystal resonance, but it's still a natural place to go given what we've done in this sequence of informal lectures so far. So, shall I make some remarks about this? Would that be useful for 10 minutes, and then we'll do oscillations. Okay. So, the proof method that I have in mind involves a particularly interesting linear map. So this is for a fixed subgroup H. Consider the linear map A. Okay, so we're thinking about representations on Rn. So I'm going to define AX to be 1 over the order of H, that's the sum of images HX over all points, over all group elements, little h in H. Okay? So this is a kind of averaging over the group operation. Okay, I take a point X and I work out where I can map it to under all these different symmetry operations. Okay, and they're all just a collection of points in Rn, and then I take that linear combination. Okay. So this turns out to be an interesting linear map. That's really the essence of the problem. Okay. And when I average this, when I carry out this averaging operation, okay, essentially this is either sort of zero or the identity. And that's one way to think about it. Either I average something and I get 0, or I average it But at every point it's actually the same as the thing I first thought of, so I just get the same thing again. Okay? So this is some kind of averaging. Okay, so we can kind of formalize this by breaking it down into a set of remarks. Okay, so where's the... I'm not quite sure what the best order is to do this, is it? I'm going to do this in a different order. So, okay. So A is a projection onto its range. Okay, since A squared is equal to A. Okay. A squared of X is, so what's A squared of X? It's A of AX, so it's A of the average. Okay, so what's the average of the average? It's the average. Okay, that's the idea. We can write that out in large amounts of detail. And this is really using the fact that H is a subgroup. Okay, so it's a sum over H's and H hats in capital H and H hat of X. Okay, but every combination of an H and an H hat is just another element of my subgroup H. Okay, so I'm still combining. I'm summing points that are mapped around other elements of H. I'm just counting a lot of them more than once. Okay. So this is a 1 over mod H squared times the sum over H and H. So if I keep one of these constants, okay, then I'm for every fixed H, as H hat moves through the group, I'm calculating a whole sort of, I get one contribution from every H hat, and that's a set of contributions that's the size of the order of the group. Okay, and they're all different to each other. So this is a 1 over mod H squared times the sum of elements H and H, okay, times mod H times HX, as it were. Okay, so as I sum over all the H hats, then I get a set of these images back again in some different order, and I've just counted each one mod H times. So that gives me something that is just A acting on it. Okay, so A squared is equal to A. So as a linear transformation, it's useful to write Rn in the usual kind of direct product of the kernel plus the range of A. Okay. And then essentially A is acting as 0 on this, as the identity on this. Okay. So we're thinking about in terms of the action of A is what it look like. So what does this range look like? So suppose X is a point that happens to lie in the fixed point space of H. Then X is fixed under each little h. So Hx is X, so that means that Ax is going to be a sum of points that are each just X. So that means that the fixed point space H is definitely contained in the range. If I start with an X in the fixed point space, then it's definitely given by a point in the ring. And then conversely, suppose x is a point in the range of the operator. So there is the y such that x is a y. Then for any element h hat, what do we have? H hat of x is h hat of a y, okay, because that was the definition of y. So that's 1 over mod h times the sum of h's and h hat hy, okay, that's just putting in the definition of a. So that's 1 over mod h times the sum of hy, because for any fixed h hat, this is just a relabeling of the elements of the subgroup H. So I've just relabeled my elements of the subgroup H. So I've got something here that is just AY again, and AY is X. So if I apply an element H hat to X, and X is in the range, then I just get X again. Okay. So being in the range implies that you're in the fixed point subspace of H. So I've got an inclusion both ways around. So in fact they're equal. Okay, so this thing here is in fact fixed point space. So I have a linear operator that is a projection onto fixed point space. Okay? So that means if I look at, so what am I trying to prove now? I'm trying to prove that the dimension of the fixed point space is equal to that sum of traces and matrices. So now consider the trace of this linear operator A. Okay, that's clearly the same as the trace of A restricted to the range, okay, by that direct sum decomposition, rank nullity formula. So that's the dimension of this range part, so that's the dimension of the fixed point. And then by linearity, the trace of A is just going to be the trace of the right-hand side, so that's 1 over mod h times the sum of the traces of the individual elements h. Okay. I still feel this should be made shorter.
Be what?
Should be shorter than this.
Yeah.
Anyway,
Yeah, with characters, it's one line, you know.
with characters it's one line.
Yes. I mean, I proved this in one line last time.
Okay.
Because you find out how many times the trivial representation of H is contained in the restriction of the representation of T to H. And so this is the scalar product between the trivial representation on H with the representation of T, and so this is just the trace.
Mm-hmm.
And you have to know this machinery about.
Of course, you have to know the machinery and stuff.
Yes. Yeah, that's true.
So
But that's still slicker. Yes. Okay. So you've seen two proofs of this now. with different amounts of technology involved. Luckily, it's always true. Okay, good. Yeah, homework problem, construct an example and do these calculations for yourself. Right. So turning now to Hopf bifurcation. So we saw last time that there were various ideas of a natural context for bifurcation with symmetry. For steady-state bifurcation, the generic case was that we had not just an irreducible representation of our group, but an absolutely irreducible representation. And having an absolutely irreducible representation so that all our commuting matrices were forced to be real multiples of the identity, guaranteed that we had a collection of real eigenvalues that were passing through the imaginary axis through 0. And they were not allowed to deviate and to do anything else. They were forced to remain on the real axis. And that gave us a steady-state bifurcation problem. There's a similar setting for Hopf bifurcation where we will deviate from this rule of having a single absolutely irreducible representation giving us the eigenvalues crossing the imaginary axis. And there are two ways in which we can deviate from that. So the first jumping off point, I think, is just to point out that there are kind of two possibilities. Okay, and this is really sort of how do we get non-real eigenvalues into our problem. Okay. So this is, I suppose these are necessary conditions for non-real eigenvalues. So with all the usual setup, I suppose I should just kind of recall the notation. X dot is f of x, and mu is going to be a collection of smooth non-linear differential equations in Rn, and I'm going to use my notation df, is going to mean the Jacobian matrix of f. So suppose that the derivative matrix x equals 0 at mu equals 0 has a non-real eigenvalue. Then we must have at least one of the following problems coming up. So either G acts non-absolutely irreducibly on Rn, or there exist subspaces V1 and V2 on which G acts absolutely irreducible and isomorphic. So this is a slightly curious statement. It either says we have a case where
You want to say irreducibly, but not absolutely irreducibly in the first alternative?
yes, I think that's what I'm trying to telescope into here. Let's make that explicit. Irreducible, but not absolutely irreducible. Yeah, let's say that. But not absolutely irreducible. That's clearer.
Jonathan, if this is a gradient system, if f is a gradient of something, so the Jacobian is a Hessian of something, then the eigenvalues are symmetric, eigenvalues are real. We can't do it.
We can't do this. No, that's right. we're now out into the jungle of non-gradient flow phenomena. Sorry.
No.
But I'm going to give you some big machetes to, cut down the creepers and all the rest of it. So it's a slightly curious way of sort of saying that there are kind of structural ways in which non-real eigenvalues come up. Either we have, and essentially because if you don't allow either of these possibilities, then you're in the case where you have a collection of subspaces on which G acts non-isomorphically on each subspace and absolutely irreducibly on each of those. And in that case, we know that the group must map that subspace into itself, and we know that the only commuting linear maps on that subspace must be real multiples of the identity, and so we're forced to have real eigenvalues. So this is, one of these must be true if you want to escape from the real eigenvalue hegemony. So if neither of these is true, then Rn is a subspace decomposition. This is a isotypic decomposition. In other words, it's a direct sum decomposition of Rn in which G acts absolutely irreducibly and distinctly non-isomorphically. Okay, so it acts by different absolutely irreducible representation on each of the subspaces Vj. So we must have the Jacobian matrix on one of these subspaces as an image that lies completely inside that subspace. And so df on that subspace must be some multiple of the identity. So in other words, the Jacobian matrix must be block diagonal and it has only red. So if you want to break out of the real eigenvalue situation, either we need group action which is irreducible, but not absolutely irreducible, or we need to have subspaces on which we have two copies of the same absolutely irreducible representation, okay? And then we can break out of this structure.
In fact, I think your first alternative should read, there exists a subspace such that G acts irreducibly but not absolutely irreducible of the subspace. Otherwise, I mean, this is a very minor point, of course, but only the theorem to be true.
That's right. Let's put that in so that it's true. There exists on which there exists a subspace V on which G acts irreducibly but not absolutely irreducible. Yes.
Well, maybe that was covered by your original definition that Reiner disallowed. So.
No, but it's the original was.
We're fine now.
Yeah.
No, I think this is the right way to state it.
So there are these two. It's what is slightly frustrating is that there are these two possibilities. So sometimes this is covered by G is said to act G simply. I'm not sure this is. So this is a kind of Marty Golubitzky and Stuart word. I don't know if other people really use this. Actually, it's said to be G simple. So
Maybe one more. I think they call it G simply if this is true. Either condition is true on the full space. Either the full space is decomposed in precisely two V1 and V2, or it's irreducible on the full space.
yeah. Yes. I've allowed myself more flexibility.
It's a minimal degeneracy. You need to have complex
Yeah.
eigenvalues.
Yes. So there are quite possibly other directions in which there are eigenvalues that are far away from the imaginary axis, and as usual we would discount those and think only about the eigenspaces which are driving the bifurcation problem. And so we're concerned with the action of the group on those eigenspaces, and then the G simple structure is that either we have two copies of the same absolutely irreducible representation of G, or we have one copy of an irreducible but not absolutely irreducible representation. Okay. So there is slightly more to the bifurcation problem, because in this context we need to think, we've thought about the action of the group, but in Hopf bifurcation problems one is looking for time periodic solutions, and that time periodicity means that there is another operation acting on our phase space, which is, there are various different ways to think about it, but there is a normal form symmetry of the bifurcation problem, which allows one to rotate the phase of solutions. There's no predetermined origin in time for these oscillation patterns. So these solutions will always come in families rotated by temporal shifts. Okay? So as well as the kind of the group structure that we put in, there is also this normal form symmetry. So this is just as in kind of regular Hopf bifurcation. So we expect a normal form symmetry to, depending on the point of view, account for or describe time shifts. So in our in nice coordinates, this will mean that we have so there's a choice of coordinates under which our vector field commutes with a normal form rotation matrix so this is a really the kind of the normal form theorem that there is a nice choice of coordinates under which the normal form for a bifurcation problem can be made to commute with the exponential of the Jacobian matrix at the bifurcation point.
That kind of looks like semi-group generator kind of thing.
Yes.
Right?
So we're supposing that we're looking for a Hopf bifurcation, so I'm thinking about having a linearization that looks like something like this in Jordan form, and this m is a half n. And this is the Elphick, Yos, Tirapegui, and somebody else, Brachet formula. So there is a choice of coordinates for my normal form calculations in which I can make everything commute with that matrix, which in our purposes is going to be just a rotation matrix. So it's going to look like it's going to be an M again.
And that's actually commutes rather than to all orders.
You brought out the exponential in a series, it commutes term by term versus the whole thing.
Right. Could there be some exponentially flat?
I think the point is whether if you apply to a C infinity vector field, there could be something which is not commuting, but it's Taylor expansion vanishes to all orders.
Yeah.
This is, but it would not be the same thing as asking that the theorem for the exponential would.
No. Right. No, I was just wondering. I wondered if the theorem says that it does actually commute, or if there is still this all orders business.
I think there's still the exponentially flat problem with this. Yeah, there are, which is why the proof for the equivariant Hopf theorem is much more complicated. And so I'm not going to do that, but I'm kind of motivating it, I suppose. under which our vector field commutes up to order n. Sorry, my handwriting is just terrible today. With that. Okay.
In fact, for all n.
Yes. Yeah. You pick an
not the same
n,
n.
then it's true for that, okay? So there is something slightly more going on for hot bifurcation in the sense that we have a I want to think about solutions which don't just have the symmetry group that I first thought of, but they're allowed to have some time shift symmetry as well. So in fact, a full kind of symmetry group that is around of this bifurcation problem is our group G that we first thought of, but then there are also these phase shift solutions. Okay. So I get a circle of phase shifts. This is a direct product. So one might sort of choose to think about these things acting as kind of pairs, G, tau, acting on a solution x of t is G x of t plus tau. And so S1 is a circle of time translation. And so then we have this RS object can be thought of as a rotation matrix that is acting either on the subspace on which G is acting irreducibly but not absolutely irreducibly, or is acting on the pair of subspaces on which G acted absolutely irreducibly. And in both cases, we end up with an action of G cross S1, which is irreducible. What I call V, if G acts irreducibly but not absolutely irreducibly, or V1 plus V2 if G acts absolutely irreducibly and isomorphically. Okay. So that's the kind of key point in all this. That the action of G might have one of two different forms, will have one of two different forms, depending on the problems you want to look at. But G cross S1 is really the kind of the more fundamental object for Hopf bifurcation. Okay?
Now, the original dynamical system was autonomous,
Yes.
right? So we always have some time translation capability in our solutions.
Exactly.
But if there's just a special role
That's right. So there's a special role here because having thought that I wanted to do a Hopf bifurcation problem, then in Jordan normal form I'm looking for a situation where my Jacobian looks like this. And then this Jacobian generates essentially another symmetry operation, which is this rotation. So this kind of extra rotation that I didn't really have before. Certainly when I was doing the steady state case, I've just got the identity matrix. So this is my new ingredient.
But maybe there's another way of looking at it. I mean, you have this time translation, and so Hopf bifurcation you can understand as breaking this time translation to a periodic. Right. But of course, if you look at the whole dynamics outside of your periodic solutions, you don't see this period which you have in the problem. You have it only near the periodic solution. And so what one is doing is one looks at this period which comes from the linearization. This will give you a period which you expect, and then you do a time-dependent coordinate transformation, which makes your system commuting with one of these matrices. And I think you didn't say it, but I think you mean a specific S. So this is not for all S, but this is a period which you want to see, right? You were RS. You did not say whether this is for one S or for all S.
I didn't.
And I think you want to have it for one S, which is a period which you want to see.
It depends on what you're thinking of. I mean, it's
Or you want to have it for all.
I think I want to have it for all at the moment.
Okay.
I mean, if you have a periodic solution, any translation of that will still be.
Sure, yes. But you want to have the whole vector field commuting with this map. I mean, you want to introduce new coordinates so that the whole vector field commutes with this map, not only near this periodic orbit, but the whole vector field. So this is what you call normal form symmetry, right?
Yeah. Okay. So I was now going to state the Hopf theorem because it gives us the kind of it shows how the structure is going to carry over from the branching lemma that we know. So there's one very minor definition. So an isotropy subgroup sigma, which is going to be a subgroup of G cross S1, is going to be called C-axial if the dimension of the fixed point space is 2. Okay. And perhaps the most interesting thing about this is the fact that my isotropy subgroups are now going to be subgroups of G cross S1, not just subgroups of G. Okay. But the idea is going to be exactly as before, that we're going to take our high-dimensional space and think about hyperplanes, which are two-dimensional, okay, and therefore and flow invariant, hopefully, and therefore within each of those two-dimensional planes, we can have exactly a kind of standard Hopf bifurcation problem that we know and enjoy, okay? And then we can prove the existence of a bifurcating branch of periodic orbits within that two-dimensional subset. So the equivariant Hopf theorem, which is Stewart and Golubinsky. It's around 1984, I think. Yeah, but okay, it's close enough.
They wouldn't know it themselves.
84, 85, I think. I wrote 84 quite confidently, and now 85 is coming. Anyway.
I remember many talks by Marty where he was saying, you know, I don't know all these numbers and these theorems were proven. They were done before I was in the subject.
But I think this one is there. Yeah, I think yes.
Yeah, no, of course this is by them, but he referred to other theorems always that he wouldn't know things which happened before him, so we can say this is approximate.
Yeah. All right. Okay. So with the usual setup, I don't know how much the standard waffle to regurgitate. So GB, one of our standardized groups, Lee group, acting since I've introduced the terminology, we might as well use it. G simply on Rn, and X will be G equivariant vector field as before. Which are on the point of the hot bifurcation. So just assume that we can change coordinates so that I have a Jacobian matrix that is now something in Jordan form with some real and imaginary parts of these eigenvalues that depend on parameters. So C of 0 is 0. I have the usual crossing condition, and I have a non-zero frequency onset. Okay, so omega mu equals 0 is not 0. Then there exist branches of periodic orbits xt periodic for period capital T. Close to 2 pi over omega 0. And having isotropy, so sigma of x of t, which is contained in G cross x1. So whenever So there is something to do here. There's quite a lot to do here, because our vector field is only assumed to be G equivariant, but in terms of my solution branches, I want to look for isotropy subgroups, which are subgroups of G cross S1. So there are problems of the kind of the normal form kind, bringing this S1 symmetry in and showing that you can, as for standard Hopf bifurcation, that you can actually realize periodic closed orbits, even though your original problem didn't necessarily have this additional nice normal form symmetry that I talked about. Okay, so there is some quite technical content here. But in other elements, it's morally very similar. So at a first glance, we are sort of moving up a dimension and saying that if I have symmetry subspaces that are two-dimensional, not one-dimensional, then they should be flow invariant, okay, which is again something that we should look at. Then I have periodic orbits lying inside those two-dimensional spaces. Okay, so it's instead of slicing my Rn into this collection of lines and saying on each line I have a one-dimensional bifurcation problem without symmetry, here we have this sort of slicing into a collection of two-dimensional hyperplanes. Within each hyperplane I have a Hopf bifurcation problem. So, are people good for an example? You look quite happy still. Okay. So, leave that for a moment. So hopefully the notation that I'm going to use for D3 will be the same as the notation I used for D3 a couple of times ago. So we have seen before that there is a natural action of D3 on the plane R2, which we kind of described pardon me, just through this identification of R2 with complex numbers we had before. So we had a sort of picture that something like this. Or symmetries of an equilateral triangle. We had a rotation element that was multiplication by e to the 2 pi by 3. And then I had an axis reflection here, that was called mx, and then there were various other reflections. I think this is another mirror, d prime, and this is md, something like that. Okay, and this natural action we saw previously was absolutely irreducible. Okay, and in fact, having been through the character theory, you now know what all the absolutely irreducible representations of D3 look like. Okay. This natural action is absolutely irreducible. Okay. So we're going to take two copies of this. Because this is part of our recipe for constructing generic Hopf bifurcation problems, is to find an absolutely irreducible representation of G and write down two isomorphic copies of that. So that's going to act on some coordinates that I'm going to call W1, W2. Okay, so these are going to be two complex coordinates for my two copies. Okay. probably just space to kind of squeeze in the generators here. So D3 is generated by rho and mx. So these are just going to act in the unsurprising diagonal fashion. And then the other thing that I have to put in is the phase shift symmetry. So I'm going to have a phase shift which also acts on my coordinates W1, W2, just as the matrix I wrote down before. So at this point some kind of I should really have written this out in a kind of vector sense. So this is starting from the two building blocks and my phase shift symmetry. And in fact, there's a swift change of variables that tidies up the notation for us. The reason for writing this down is to make it completely obvious that I'm taking two copies of the absolutely irreducible representation that you know and love. Okay, but in fact the nicer way to write this thing is to introduce some coordinates z1 and z2. So z1 is 1/2 w1 bar minus I, w2 bar. Z2 is 1/2 w1 minus I, w2. Okay, so it's just a linear change of variables. Okay, and that means that I'm going to write rho acting on z1 and z2 e to the minus 2 pi by 3 z1 z2. My reflection symmetry mx on z1 z2 just becomes an interchange z2 z1, and then the time shifts I'm now calling tor phi act in the same way, so they act diagonally now. And so tor phi is exactly the same as R. Okay. So these things generate an action of D3 cross S1. Okay, so this is just a tidied up version. And now we need to look at this two complex dimensional eigenspace and see if we can find any one complex dimensional, two real dimensional hyperplanes that have isotropy subgroups that fix them. So there are three group orbits. conjugacy classes of. Let's have 3. Non-conjugate. The axial isotropy function. So there's an isotropy subgroup, which is the group generated by the composition of a time translation of 2 pi by 3 and a rotation. Okay? So if I take a point z1, z2, okay, and I first do a time translation of 2 pi by 3, and then I do a rotation, then in the first factor, those two factors cancel. In the second factor, they don't. So this is going to fix points on the form z, comma 0. If I think about the isotropy subgroup generated by reflections, that's going to fix points that are the same in both coordinates. And then the third one is slightly less obvious. But if I take a time translation for half a period of my oscillation, so phi equals pi, okay, and then I do a reflection mx, which changes my coordinates over, then what I've done is to introduce a minus sign here. I've got an e to the I pi in both factors, and then I flip them over. So that fixes things that were different by a sign in the two coordinates. So sigma 3 is an isotropy subgroup that fixes points that look like z, comma minus z. And one can check that these three are not conjugate isotropy subgroups. So these points lie on distinct group orbits. I can't get from one of these points to another one just by applying some symmetry operation. Okay? So these are...
Jonathan,
Yeah.
it seems like there would be a closely related cousin to sigma 1. Maybe it's conjugated, but if you compose rho with tau sub minus 2 pi over 3, you get a fix of 0 comma z, don't you? But then that's nothing new apparently. Or
That's, yeah, so that's related by the mx interchange symmetry. Means that whenever I've got this hyperplane, there's always another one on the same group orbit that's 0 comma z. Yeah. So these three are I can't get from one to the other through that kind of argument. They have distinct dynamics. So yeah, so whatever this one does, your one will have to follow in terms of branching behavior and stability and this kind of thing. So, what do we want to know about these? How much time do we have? So the last thing I was going to do, so we can show that they're different. For example, if we wanted to look near the bifurcation points to construct the most general equivariant vector field, okay, for this bifurcation problem. So that would be a four-dimensional, four real-dimensional vector field in my two coordinates z1 and z2. Okay, that would show that the bifurcation behavior for these three branches would be different. That's not, and that follows things that I did last time. There's an interpretation which is quite nice here, I think, to sort of get a handle on sort of physically what these three different solution branches might mean for a particular problem, which is an interpretation in terms of coupled oscillator dynamics. I thought that might be a fun thing to do, to sort of say what kind of oscillation patterns these three might really look like. And that might be a good thing to do and then finish, which might take another 10 minutes or so. Is that okay?
Double pendulum. So like a double pendulum would be a couple oscillators or something different.
Something slightly different, but still. And in fact, I've just realised I have some. There are some movies that could go with this, except I didn't bring my laptop down. But I can show them upstairs if people want to crowd around a table. They're not my movies, they're much better than that because they're real biology. So it's kind of, anyway, I'll do some more sums, okay, and then I'll kind of do the advert for that.
The movies go on the blog, or they?
Well, they're private property of somebody else.
Yeah, but I mean,
They're not my movies.
would you need to get permission to put the movies on the blog?
I could probably post a link to the
Yeah,
guide's
that might be-
homepage. I think that might be
good.
slightly better. But if you're watching this, they are terrific movies. Thank you so much for doing the work. And I'm about to cite your paper as well.
The director of the Institute has been encouraging people to use social media more. So next time you might find the audience answers back when you say things like,
It is completely incidental that I've just exploded into coffee. Okay. A couple of oscillators right now. So what I'm thinking about is, based on our kind of D3 symmetric picture, why don't we take three kind of independent chemical reactions, or kind of, blobs that have some internal dynamics, and then have some weak bidirectional coupling all to all in this case. Okay, so this is bidirectional all-to-all coupling, and there's some kind of internal state given by some quantity xi for each of these blobs, and so that might be a kind of list of chemical concentrations at a time t, and so it's a vector in some rk, and that's for each of these solutions. Okay. And maybe they're sitting on some substrate that's providing nutrients or sort of a driving chemical concentration to sustain a reaction. Okay. So I have some objects which are kind of naturally prone to undergo, some kind of time periodic behavior. And then the question is, if I couple them together, then what kind of patterns of oscillation might persist or might sort of arise through some instability that wasn't there before. So one can imagine a state where these things are prone to oscillation, but they're actually in a regime where they're at a steady state. Okay, and they're coupled together, and you change some external parameter like pH or temperature, and they suddenly sort of decide to undergo an oscillatory instability. That oscillatory instability is then constrained by the fact that there are three of them and they're bidirectionally coupled. And one can ask, what are the kind of natural ways in which these sort of oscillations will coordinate across the three lumps, okay, these three pieces of chemistry. So in a very general case, there are going to be some differential equations describing the dynamics, and again, the external conditions are thought of as held constant. So there's some governing chemistry, and the governing chemistry for each blob is the same, which means that these F's are permuting their arguments, okay, and then the bidirectionality and the symmetry of the coupling means that I can interchange the second and third components, okay? So x0 is equally influenced by x1 and x2. So if this is f of x1 and x2, then that should be x0. And then, without lots of generality, let's put our basic equilibrium point at the origin. So x naught x1, x2 equals 0 is an equilibrium point. And then for stability, our Jacobian matrix is going to look like, in block diagonal terms, ABB, BAB, BBA. Okay, so this is going to be a 3K by 3K matrix. Okay, so those entries, A is kind of dx0 dot by dx0, and B is dx0 dot by dx1, etc. So the eigenvalues of J are those of A plus 2B and A minus B twice. Okay? Because A minus, this is a, what's the word? Circulant, block circulant matrix. So this is A plus omega squared B plus omega B to A minus B. Omega is so there are two kinds of instability from an equilibrium solution for this kind of system. Either I can push an eigenvalue of A plus 2B through 0, okay, or I can push eigenvalues of A minus B across the imaginary axis. And the interesting case is going to be the one which involves A minus B. Okay. Suppose we have a hot bifurcation through I omega 0 being an eigenvalue of A minus B. Let little b be the associated eigenvector. And then what we're going to do is to essentially recover the structure that we've just done in the abstract. So if I've got little v is an eigenvector for A minus b with eigenvalue I omega 0, then big V1, I'm now going to stack these little eigenvectors on top of each other. So then in the standard way, we perform some center manifold reduction. So I'd write my full state space variables x0, x1, x2 looks like some amplitude z1 t times this vector v1 plus another independent amplitude z2 of t times big V2 plus complex conjugate because the x's are reals and the z's are and v's are not. So then there's a group action on my center manifold coordinates z1 and z2, which is defined via the action of D3 on the kind of the real state space, the original state space variables x0, x1, x2. Okay. So we had some kind of permutation possibilities, okay, of permuting my x's around, or just keeping x0 where it is and flipping x1 and x2. Okay, and that induces an action of D3 on my center manifold coordinates z1 and z2. So we have something like rho on x0, x1, x2, x1, x2, x0. So that means that I can define an action of rho on z1, z2 by saying z2 via z1 rho of v1 plus z2 rho of v2 conjugate should be what I'm going to call rho of z1 v1 plus rho of z2 v2 plus conjugate. I'm going to need this in a moment, so I'll rub it out first. And then rho actually on V1 is just given by, so it's just permuting the coordinates, and that's essentially the same as multiplying everything by a little omega, which is like 2 pi by 3. And rho of V2 is omega squared times V2. So this is just kind of checking what happens to the coordinates. So the natural thing is to define rho acting on Z1, Z2 is omega Z1 recall that omega is just e to the 2 pi by 3, a shorthand of that. Similarly, looking at the action on the eigenvectors, we get the action of the reflection symmetry is the interchange of Z1 and Z2, as we've had before. And this time translation symmetry is just given by rotating everything by some factor. Just as we had before. Okay? So in other words, for this bifurcation problem, setting everything up so that it was D3 symmetric means that when I think about a bifurcation involving this eigenvalue of the matrix A minus B, which gives me eigenvalues with multiplicity 2 for this Jacobian matrix, means that on the centre manifold, I naturally have the action of D3 cross S1 that we had in an abstract sense half an hour ago. Okay? And we know what the branches are. Okay? So now I can go back to my list of bifurcating branches. Okay? So the first one looked like Z comma 0. That was our first C-axial or fixed point space for a C-axial isotropy subgroup. So this is going to be a collection of chemical concentrations that looks like Z of T times V1 plus 0 times V2. That's complex conjugate. So this is going to look near the bifurcation point like some R0 e to the it. This is some time periodic oscillation multiplied by an eigenvector V1 that looks like little v omega v omega squared v. That's complex conjugate. Okay, plus nonlinear corrections to this. So this omega is a factor of e to the 2 pi by 3. Okay, so we can simplify this a bit and say this looks like R0 multiplying e to the it times some constant eigenvector little v. This is an e to the I t plus 2 pi by 3 times little v. And this is an e to the it plus 4 pi by 3 times little v. Okay, so this is just a kind of the linear term in what this solution looks like. And the solution components have the same structure for the concentrations in each of these three entries because each of them is multiplying the same eigenvector little v. Okay, that's the eigenvector of the A minus B matrix. But there's a phase shift in the response between the three components. Okay, so you have to wait a little bit between when each of these kind of peaks. Okay, so this is plus complex conjugate. So we think of this as a kind of cosine wave, and if it peaks at time 0 in the first component, then it's going to peak at time pi by 3 later, 2 pi by 3 later in the 2 component, and then 4 pi by 3 later in the 1 component. Okay? So this is a kind of waveform that rotates around between the three objects. So in terms of the dynamics of the problem that you'd actually see, we have something that looks like a rotating wave. So there's a sort of series of there's a kind of peak here, a peak here, and a peak here. So if you did a kind of time trace of the concentration of each, some chemical in each of these oscillators, you'd see a sort of peak in one of them, and then this would have the same shape, it's the same waveform, but the solution for oscillator 1 is shifted in time, and the solution for oscillator 0 is then shifted in time further. Okay? So you see a peak here and then a peak here and then a peak here. Okay? So it's a rotating wave pattern because it's the same waveform, but a kind of a temporal shift is equivalent to a spatial rotation of these three oscillators. Okay? And we've made this exact connection by kind of working everything through. And so this has the symmetry rho. Okay, remember this was the elements that generated our isotropy subgroup, and this says that the operation that fixes these points is a combination of some time shift symmetry and some spatial rotation. Okay? So to go through the other two slightly faster. So the second case we have z comma z. So here I've got x0, x1, x2. Looks like z1 equals z2. So this is times v1 plus v2 plus complex conjugate. So this looks like z of t into twice little v minus little v minus little v. That's complex conjugate. So whatever this looks like, okay, this is the same little v here. I've got an oscillation pattern that's kind of twice as large in amplitude in x naught, and then for x1 and x2 it's the same, but it's out of phase. Okay, this is a kind of time shift by a factor of pi, half a period. So if I plot the kind of the waveforms for the three oscillations, then I've got something that's doing a kind of large amplitude oscillation in 0, and it's doing a smaller antiphase oscillation in 1, and a smaller antiphase oscillation in 2. Okay. So in other words, whenever sort of 0 is sort of up, doing a maximum, the other two are kind of down. Okay. And then it all reverses. So this one kind of comes up, the other two go down a bit, and then these two come up, and this one goes down further. Okay. And this pointwise in time preserves this NX reflection symmetry. And then the third case, z minus z, got x0, x1, x2, looks like, so this is a big V1 minus big V2 plus complex conjugate plus higher order terms. So this looks like z of t times, and this is the imaginary part of the little omega times kind of 0 v minus v again. So this is interesting. This says that, in some sense, what's happening in the 1 and 2 components is out of phase with each other, and there's something that's sort of much smaller happening in the top components. Okay, so we don't have a particular clue. There are some nonlinear terms to put into all this, but if this is some waveform y of t, then it's not obviously connected to x of t, but this one must be a waveform that looks the same but is just pi out of phase with it. But what's interesting is that I've got something that is symmetric under mx and so this is the one that has the symmetry reflect in x and wait for half a period. So if I reflect in x and wait for half a period, then I get something here where these two are still half a period apart. Okay, but I have to have the same, but they're the same total influence on x0. So y of t must be a solution component that stays the same when I wait for only half a period. And that means that y of t must in fact be oscillating at twice the frequency that you thought it was. So that means that the solution waveforms for this problem, or for this solution rather, are that whatever 1 is doing, 2 is out of phase with it. Okay. But then, because these are both influencing 0, 0 is doing a kind of smaller amplitude oscillation, but it's doing it at twice the frequency. So this is a collection of 3 blobs where these 2 are out of phase. And this is. So these 2 are going sort of up and down and then switching, okay, and each time they come up they kind of kick this one that they're connected to. And so this one is being kicked repeatedly by this one, and then it's being kicked after half a cycle by this one again. So actually it's receiving twice as many kicks as these 2 are providing each. So it's oscillating at twice the frequency. It has twice the response that these 2 do. So this is a slightly unexpected solution result, in the sense that it's not completely, it's not maybe something we expected, to have solutions that were forced to oscillate with different individual frequency components. Experiments are slime. This is physical being 223. So the biological version of this is to take 3 Petri dishes with some gel substrate and some little channels between them, and to put slime mold colonies into each dish, and they, there's still slime mold sort of filling up the little channels, and they have this sort of aggregate chemical signaling mechanism between the different colonies. So they know sort of roughly what state the other colonies of slime mold are in, and they have a sort of collective, large-scale oscillatory response to the chemicals that they produce and the nutrients they use up. And you find that they fall into these different collective oscillation patterns as you vary the different external parameters like pH. And so that even biology is constrained by symmetry.
What kind of time scale does that all play out on these populations of the slime mold? Very slowly varying.
I think it's sort of tens of minutes rather than hours. So it's still, I mean, you find that you warm them up to about 40 degrees or something, so that they're working a bit faster than they would be otherwise. So I can show you the movies.
Great.
Anyway,
Thank you very much, John. Thank you for all your effort over the whole series, because you'll be away for a while.
yes.
So, the end of this kind of tranche of.
Absolutely. There are plenty of other people to take over if the organisers wish.
Okay, well, a round of applause for your work.